Okay. Okay, then welcome to my small little presentation about safe robot navigation via multimodal anomaly detection. We will have a small introduction. After that, we will talk about the data set. After that, we will talk about the various methods that were used in the paper. Then we will look at the results and finish with a conclusion. And after that, I will give you a few references if you want to look into things further. First, to have an autonomous robot, the robot has to be aware of his environment to navigate safely through it. So mostly he does this by creating a map of the environment using his onboard sensors. So those are most of the time LiDAR sensors. Those are pretty popular with self-driving cars. And depth cameras. Fun fact, Tesla uses depth cameras over LiDARs. When creating those maps, obstacles are often simply considered as the presence of geometry. So if there's a wall and the laser bounces back from that, you have a geometry and you can detect an obstacle by that. This works well in man-made environments, for example, industrial facilities or storage facilities. But it fails when we go into outdoor environments. To see what such a mapping procedure would look like, we can see look at this image. Here we see a coast map, it's called. So we have our obstacles. Those are represented by the small black dots. Those were recognized as geometry or obstacles. And those colors here indicate a cost map, so we already have an evaluation of the map. And this means that those purple lines here are not traversable because there are walls and the robot can't move the walls, sadly. And the other colors just indicate currently the amount of movability the robot has inside those areas. As already said, the autonomous robot has problem navigating in natural outdoor environments because he only uses geometry, and in outdoor environments, perceived geometry cannot necessarily be assumed to be rigid. For example, a robot could easily push through tall grass or leaves hanging from a tree. And on the other side, flat geometry cannot always be assumed to be traversable. For example, bodies of water would have a flat geometry, but we don't really know how deep they are, and if the robot walks through them, it might be fatal for him. To solve this issue, we want to categorize the terrain in traversable and untraversable. We will call traversable terrain positive, so positive samples are samples of traversable terrain, and we will call untraversable negative. So untraversable negative samples are untraversable terrain. We assume that semantic information is necessary in addition to geometric information. So geometric information is geometry in the shape, for example, of point clouds or depth sensors. And semantic information is, in this case, currently color. Analytical methods are not tractable on this sort of problem, and supervised machine learning approaches would require large quantities of data. And most of the time, this data would have to be labeled by experts, especially if we want to build a robot in a new kind of environment. For example, for planetary exploration, you would have to employ some astrogeologists to label our data set to know where the robot can walk on Mars or the moon or something like that. The solution to this problem is that we use unsupervised learning to learn a distribution of positive samples. So negative samples could be detected as anomalies. So this all boils down to an anomaly detection problem. And we could easily collect positive samples by just teleoperating or remote controlling the robot around safe environments that we already know the robot can traverse. The data set that was used in the paper was collected by using a four-legged robot called Animal, and it used an RGB camera, so a camera that collects RGB images, so between blue, normal color images, and depth images. When we let the robot walk through the terrain, we use visual SLAM. So SLAM is an algorithm to create a map and localize the robot inside the map at the same time. So when we let the robot walk through the terrain, we project the position where his legs touch the ground onto the images. And then we can take the patches where the legs touch the grounds project onto the images and use those as positive samples for our data set. A small negative, a small amount of negative samples was labeled by hand for having a test set. And the data set contains various conditions. So a sunny afternoon, I think, fire, rainy condition, after the rain, a wet condition, and twilight. So very different light, very different light conditions. In the paper, there were different input modalities used. The first one is RGB, so just normal color. After that is depth, so the distance of a point to the camera. The next one is gravity aligned depth, where we just split this this direction into a horizontal and a vertical direction, again relative to the camera. We also in the paper they also use gravity aligned surface normals, so the normal vector of a geometric surface, for example, of a flat surface, the ground, for example, the normal vector would just point straight up, and we use and in the paper they also use the surface normal angle, so the angle of this normal vector. When we actually want to implement that for our robot, we use this anomaly detection to classify images, to classify patches of the images. So we segment our image into small patches and classify each of those patches using the anomaly detection, and by that we can create a mask of an image where each pixel would have an anomaly score, and by that we can create an anomaly map of our environment. Each approach presented in the paper used a decision criterion. So using this decision criterion, we can classify something as an anomaly or as not anomalous. All approaches shared a feature encoder, and every approach was trained using only positive examples. And real MVP and deep Spdd are evaluated both with and without a pre-trained feature encoder, and the feature encoder was pre-trained using the autoencoder. The first method that was proposed is a traditional autoencoder. So we just built our autoencoder, and the assumption we make is that the autoencoder would overfit on the positive data, so it learns the distribution of the positive data. And when we wanted to reconstruct a negative sample, it would do so with a lower reconstruction accuracy. So we could just use the reconstruction accuracy as the decision criterion. In the actual implementation, we would have to find a threshold value, which we would use to then classify the samples into anomalous or not anomalous. The next approach that was proposed is the deep Spdd approach. I forgot what Spdd stands for, sadly. And what this does is it learns a minimal radius of a hypersphere with a fixed point c. So we have to choose a center point for the sphere before we start training, and it also should not be 0 because in the it should not be 0. And every point outside of this hypersphere will then be considered as anomalous. There are two different loss functions. It can be used for training this model. The first one is soft boundary, which also tries to minimize the radius. It also tries to minimize the radius. The hard boundary loss just tries to minimize the distance to the center point. And then the decision criterion we use to classify anomalies is, again, the distance to the center point. So everything outside the radius, again, should be considered as anomalous. Here we can see a simplified model of this deep SPDD. We have our data set and the feature encoder that's shared by all models then learns the mapping to a latent space. And inside this latent space, we construct this hypersphere. So those points here would be anomalous and those not. The next approach is the real NVP. This is a type of normalizing flow, and it works by learning and bijection, so an invertible transformation G, which doesn't change the dimensionality, but we try to map the distribution in the latent space into a known prior, for example, a normal distribution. And we use a loss function that's the log likelihood, but we have to use the reparameterization trick. And it looks like this. And we can just use the log likelihood as a decision criterion. So an anomalous sample would have a low likelihood, and a not anomalous sample would have a high likelihood, or at least a higher likelihood. And this is a simplified model of a real NVP. We again have our input, and we use the feature encoder to encode it into the latent space. And inside this latent space, we have the normalizing flow, which learns a transformation from this distribution to a known prior. The results can be seen here. We can already see that the NVP is the best performing, and it also one of the most consistent ones. The autoencoder performs a little bit worse, but it approaches the performance of real NVP. We can especially look at how bad only color is at detecting anomalies, and how much it improves when we add those two types of information together. The deep SPD performs the worst, and is highly inconsistent. For example, the depth and the normal vectors perform better than anything else in this of this model.
Could you just explain the letters, the D, the G, and the N, because I just forgot.
Yeah, RGB is RGB is normal color. D is depth. G is gravity aligned depth, so vertical and horizontal and vertical.
That one.
Okay. So the rest is clear.
Thank you.
Okay. Yeah. This is what the anomaly mask would look like when we using a real NVP. So those reflections we can see here, those red spots will be classified as anomalous. And again, this has been generated by segmenting the whole image into patches and then running the anomaly detection onto those patches. And we can create a mask by using that. And we can also see the stride here. because we have to convolute over the image. This already leads us to the conclusion. So we now know that both semantic and geometric information is necessary for good anomaly detection. We also know that feature engineering actually is important, so we can't just leave that out. And future work could focus on improving performance by injecting negative samples, which has been proposed in the paper, but sadly there hasn't been any paper about it yet. And also papers could focus on researching the topic of automating the collection of positive samples. For example, the robot could try to explore his environment and doing that collect safe samples. If you want some reference for further reading, this paper here is more about the way the data was collected. The second one here is the paper about deep Spdd, and the third one here is the real MVP paper. If somebody reads this paper and understands it, he might hit me up because I don't really understand it yet. And also the original authors of the paper presented it themselves, and this is the link to that, and it's highly enjoyable. Especially you see a lot of videos where the robot does it in real time, like navigate. And then thank you for your attention.
So it was kind of unclear for me from the paper. Will the when the operator's like driving the robot, or what exactly are the images going into the model? Is there like a forward-facing camera, or is there just cameras that are attached to the legs looking downwards?
No, the robot has a downward-facing camera, so you can basically think of it as a dog, and it walks. And we have images of every step, you can say so. And the robot also knows where his foot are relative to his camera. So we can create this map and basically map each image to a spot on this map. And because we also know where the legs are, we can map the positions of those legs to those images, or to positions in the images.
Okay.
Okay, cool. I just got a weird
Yeah.
message from Zoom. But this is this whole topic. If you want to look into it, it's SLAM. It's simultaneous localization and mapping, and it's a huge field, and it's really cool and really complicated.
Yeah, but it's it seems like it's what do you call it? It's not like an image classification. It's like, it seems like a 3D map.
Yeah. It used an intelligence camera, so we have a depth image in front of our robot, you could say. And the SLAM algorithm then takes those point clouds, they are called, or those depth images, and builds a map out of those.
And is
this is like a 3D map.
Yeah.
Okay.
And the output of the model is it classifying each like point on the map, or is it classifying? I looked earlier like a segmentation, or yeah, in one of the images you showed, it looked like a segmentation problem.
Yeah, but there are, on the one hand, there are segmentation networks, I think they're called, which like do a pixel-wise classification. But this is actually not a segmentation network, or whatever it's called. This one, you can think a little bit better about it if you think about convolutional layers, because it also has this kernel, and it walks over the image. And for every patch or kernel or whatever, we generate an output like on a new mask, and we can use that to classify anomalies. So after that, we should have a heat map of sorts, and then we could threshold all the values for a specific specific threshold, and then all values that are higher than this threshold would be anomalous, and every value be lower than this threshold would be fine, not reversible. Did this clear things up a little bit as far?
A little bit. But it's for an image, not a 3D map. Well, yeah, I'm a little. Yeah, I'm stumbling, but I'm not sure.
We have a image. We have a 32 by 32 image, and we have our 3 channels. So we have a 32 by 32 by 3 input, just for the RGB image. And when we, for example, use depth, we add 1 channel to this image. So we build up this stack of channels for the image and use that as the input for the model.
Okay.
Yeah, it's really complicated. At least for me, it also felt very complicated to read and try to understand how it would look like in the end. So I think I got it a little more now that you explained it so much. But it's still, have you worked with these sorts of problems a lot before?
Well, I work in a robotics lab, so sometimes, but the problem is it basically boils down to having an image, having a position of a robot, and then projecting this 2-dimensional image technically onto a 3D surface. So you have the position of the robot inside a 3D map, which has been generated by those depth images and point clouds we were talking about. And we also have the RGB image, and then we have to project, for example, each pixel in this image, technically we have to project it onto our 3D surface. For example, a very simple example would be that we have our camera and we have our image of a wall or something like that. And we have the wall here. And we could technically just project every pixel directly in front of it. So we would project every image directly onto this 3D map, if that explains it a little bit better.
Mm-hmm.
Yeah, and then it gets complicated as soon as you like start rotating the camera or tilting it and don't have flat surfaces. But that's all part of this SLAM algorithm. Or like this SLAM is not an algorithm, SLAM is a problem, but like solutions to this SLAM problem. There have actually also been a few AI approaches to this, like taking in point cloud information and using this to get a position inside this map, inside the map.
Cool, thanks. Need to think a little bit more about it, but becoming clearer now.
Okay.
I seem to be having connection issues, but I have another question. So the robot's seeing like forwards, and the operator's driving it around and showing it places where it's like able to go, showing it positive samples. But I mean, during the time where the operator is driving it, the operator will probably be able to see places that are impassable. It just won't go over them.
Yep. There are those connection issues.
I'm still trying to figure out where the fault detection, sorry, what they call it is fault detection, I think. And I'm looking at the paper itself.
Can you tell me the page?
So I'm just looking at the abstract for now. It's called anomaly detection, not fault detection, sorry. So I'm still trying to figure out what the anomaly detection part is over here.
Okay. We could have two approaches. We could, for example, train a classifier which has two classes and then just train it on that. This is, as already written in the paper, this is a bad idea because we would have a giant data set to have all the different types of anomalous environments that could happen. The other idea is that we just learn a distribution, so a probabilistic distribution of all positive samples. And then we would technically have a two-class classifier, one-class classifier, which only detects, is this sample that we have inside our distribution? And if it's not inside our distribution, it's anomalous. So we can implement a two-class classifier, or technically a one-class classifier, as an anomaly detection problem.
Yeah, that clears it up quite a bit. Yeah.
Okay, cool.
There does seem to be quite a bit of work that needs to be done to make sure that, you know, if there's something within the distribution itself and there's something outside of it, then, you know, needs to be able to understand properly what's outside the distribution itself.
That depends. For example, if you would want to detect all anomalies, like you want a classifier that says this is anomaly, and you would learn the distribution of all anomalous environments, this distribution would be way more complicated because there would be fire in there would be deep bodies of water in there, and I don't know, sharks or something like that. And this would be highly complicated because we have to think about all the things that could be anomalous. But instead, we can just learn the distribution of all positive samples because we already know what kind of samples are in this distribution. And this makes it a lot easier for us to detect anomalies because we can just detect anomalies by saying that they are Jesus Christ. We can detect negative samples by just saying that they are not positive samples.
Right, yeah, that really does clear things up a little bit more for me. Yeah.
Okay, cool.
Yeah, this is just a different way at looking at things that I have never considered before, that you just really concentrate on the positive things, but it makes sense with the robot because you don't want to drown your robot every time you want to get some samples.
Robot to stick to the rivers and streams that it's used to.
So do you have any examples of surfaces or like areas that fail in these classifications, so that the classifier says, oh, it's fine to go there, but it's actually not fine? Or is there anything in the paper?
There is not anything in the paper. What I thought might make the detection fail would be something like, well, it depends on how good your positive samples are. And you also have to differentiate between false positive and false negative. And you have to find a trade-off between what's worse for you. But for example, if you would train your positive samples in spring or something like that, or in summer, so everything is green and happy and healthy, and then you do the same thing in the winter, where like traversable surface can be flagged because of the snow, or if like all bushes are not longer green but brown because of the branches and stuff. I think that could make the robot fail because we would have actually a little bit broader data set that we train for the positive samples. So we have to again have a good domain knowledge where we want to use our robot.
You'll have effectively teach your robot to stay inside during the winter.
That would be one solution. But that's again where this like it was mentioned as topic for further research, where you could like program the robot to automatically explore his environments, and while exploring his environment, he already collects a bunch of positive samples because he knows where his foot is and he knows where his foot is in an image. And during this exploration, he would get more confident about his environment and to know what would be anomalous. So this might solve the problem. And you would have to try to keep him a little bit curious, maybe. But this automation of the collection of positive samples is like this one thing that would probably solve that. Or we could just keep him inside. It's currently the better idea anyway. Shit, I forgot to add him.
For the autoencoder, it seems like to me I didn't see exactly like the specific way that they implemented it, but it seems like how overfit they make it will have like a large impact on performance. So did they measure just like how well they or how strongly they overfit?
Sorry, I was currently writing a message. Can you please repeat yourself?
Oh, so the autoencoder, in order for it to like work well, it has to be like overfit, but not too overfit. It's like you don't want it to overfit and just be able to like perfectly reproduce and memorize all of your training samples. But
yeah,
you know, you want it to be overfit enough where it's like it won't be able to do as well. You know, it'll be able to recreate like a summer scene, like you said, but won't be able to recreate a winter scene as well. Noticeable. So there's kind of like a Goldilocks zone, I think, for like making for how much you make the model overfit the data. So did they say how they did that?
No, sadly not. But you also, when you look at autoencoders from a more theoretical view, you have your like your is the posteriori, like the distribution of your data space. Let's call it px. And you can think about your encoder technically as learning a mapping from px to the latent space pz. So you already have this idea of your encoder technically learning a probability distribution. And you want to learn the distribution of positive samples. So you just have to, this is meant when they say they want to overfit on the positive samples. They just want to learn the distribution of the positive samples. Yeah.
I see what you're saying, but I don't know. Graph.
Are you talking about the autoencoder?
Yes.
Yeah.
Okay. Sorry, I'm really sorry. I thought the meeting was at 9 my time, but it's at 8. Really sorry.
Well, I'm actually missing lasagna day today.
Yeah, I was just thinking it's like my idea of like, you know, maybe they made it overfit too much or too little somehow, and that could be responsible for like why it performed so poorly on just the RGB image.
Yeah, I know what you mean. Because when I tried to implement it myself and like best practice, put batch normalization layers and dropout layers in your model to prevent overfitting, I just removed all of them because I thought it would make it better, and it didn't. At least not on my validation set. On my training set, it made it better. But yeah, I know what you mean. But like why it performs so bad at RGB is mainly because it's missing this geometric information and it's only working on semantic information.
Okay.
You know,
But
I was
isn't, oh, sorry.
no,
Go.
Julia, please go ahead. No, Julia, it's okay.
I was just making a comment that actually maybe it's not that important that it's bad on the RGB, because like I guess usually you have the depth information. Or do you have robots that don't have depth cameras?
Well,
not?
I try to build one myself, and depth cameras are expensive. So
Okay.
I don't have
Okay,
one,
good.
but in usually industrial environments, they use depth cameras.
Yeah, no, I was just thinking about that, you know, looking at the table, you know, table 1 that shows the different sensor combinations there. And I was just wondering about how, you know, consistently everything that, if you compare to the third group, that it is the combinations, for example, of the normals that don't have the RGB, they seem to be okay, but consistently, when you check the same group with the RGB information, it's way much better. And I was just thinking if it is, yeah, because it requires of the, you know, being able to process it semantically. But I was thinking about whether it would be the same type of results, like if we would see that the RGB plus the gravity aligned depth and the gravity aligned surface normals would be the also the like the top result under different conditions, because this is for sun. Do you know if does the paper say like how are the results under the other conditions?
Sadly, no. The paper is sadly not really clear about how it performs on other data sets. And again, I tried to reproduce the results and I didn't really manage to do it. So it's very and I used the code of the original paper too for that. But it's very I have the theory that it performs worse under certain combinations of the sensors, because the model actually lacks the what do you call it, the capacity to work with this abundance of information. So it just kicks those out. It makes it easier for it, and therefore works with less information than it would have if we would use a different combination of sensor modalities.
Did you try to replicate the results in this paper?
Only for the well, I once pulled the repo of GitHub, and I failed with that. Like it ran, but it didn't really get the results. And I also tried to implement the autoencoder one with the data set that was used in the paper, and I didn't really manage to do it. So I got the top one I got was 80, and that was after fine-tuning every parameter for 2 weeks or something like that. So I don't really know how they got to 92% accuracy with the autoencoder. I really don't know.
Okay, but their code in the data set is all online, and in theory, you should be able to reproduce with only a single click. Or
I didn't do it, so you could try yourself. Would be very thankful. My boss would be very thankful.
was also really, I don't know if you already discussed that, but I was really surprised by the results between no pre-training, pre-training, and fixed features. Did you already discuss that?
No.
Not really? No, okay.
But They
I
also
would say that in
talk
general,
about it.
pre-training a model, but allowing the weights to still be updated would always be better than pre-training a model and then having fixed weights. But I think results show otherwise.
Yeah.
And I think that's really strange. Like, to me, it makes me believe that the authors made some mistakes here and there in their implementation, because I've never seen those results before.
Yeah, you're like, I hadn't realized that, but yeah, it kind of doesn't make sense, right? I mean, how come are the results after pre-trained results are pretty much consistently worse?
Yeah. So it might be outfitting, or
maybe we're teaching our little robot something that he shouldn't do. It's the wrong kind of training.
Yeah.
I think they actually wrote something about it on the results, but I can't find it right now. Oh, yeah, here. The higher performance of the real MVP version trained with fixed feature generator weights we assume to be caused by joint distribution learning of multiple modalities. Some parts of the actual underlying distributions are ignored without fixed features in favor of mapping to a simple posterior distribution where higher likelihood can be achieved.
Yeah, I do remember reading that.
Where are you? What point? Oh, yeah.
Page 5 under C, numerical evaluation.
Oh, yeah. All right, so if I understand correctly, they say that if you don't fix the weights, the model will ignore basically some modalities. And with modalities, they mean like RGB input or depth or...
That's how I understood it. I mean, the model always tries to make it easy for itself.
Yeah.
Also, I think that real MVP is not really trained with any sort of it's not really trained on any sort of reconstruction or something like that. And maybe that's why it removes important features and just drops them. But I really have to look into real MVP or like normalizing flows in general. They look really interesting.
Yeah, but I think that's actually a very important point to keep in mind, that sometimes the pre-training makes it worse, and to look out for those traces that the model does that, or any other model could also do that at some point.
A little bit scary, you know, because how would you know it?
So it's like very in contrary to all those language models that just work so much better when they're pre-trained instead of without pre-training.
Yeah. I mean, it's not that it's worse without pre-training. I'm sorry, I interrupted you.
Yeah, no pre-training is not necessarily better than... Well, for MVP, it's better. No, sorry, no. Yeah, for MVP, it's better to have no pre-training than to have pre-training. I think that can make sense. If the pre-trained weights just find different features than you need for classifying or for finding anomalies, then that's not really that strange.
But here again, it's interesting, like the distribution of where it performs worse than before. For example, it performs basically the same for RGB, but much worse for depth.
Yeah. Really weird.
But it's that's a reoccurring problem, I think, because most people don't really question why it performs worse. They just see the model as a black box.
Mm-hmm.
Guys, I'm sorry, but I have to leave. But I really, really appreciate the presentation, Max. I think you did a great effort on 21 slides. Like, wow, you get the cake over there. But I look forward to our next meeting. Yeah, let's talk on Slack because I will have to leave.
All right.
Sure.
Sorry.
Bye.
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 Oh. Eric also disappeared.
Yeah, Max, I think this was really a great job because I went from not understanding much in the paper to understanding a great deal more with your presentation and your explanations afterwards.
Yeah, thank you.
Thank you.
Well, it's probably a bit advantageous if you know a little bit about robotics.
Yeah, I'm really, really sorry I missed your presentation. I heard it's good.
It's okay, I can send you the slides if you want.
Yeah, if you can send me the slides, it would help. But anyway, thanks.
I mean, next time we can hear something about natural language processing.
Yeah, I think I will look at maybe 2 papers. I think we already posted 2, and then make a little poll like what you want and like which one I should pick, and then I will try talking about language models.
Sounds great.
Enjoyed the presentation.
So I guess I'm gonna stop recording.